This is Unit 7, Lesson 1, an Introduction to Differential Equations. Before we started studying calculus, you guys were solving equations and our solutions were numbers. So now what we're going to do, talking about differential equations and comparing it, we're going to get a function as an answer. So a differential equation is any equation that involves one or more derivatives of a function. So what we're looking at is we're looking at equations that describe relationships on rate of change. So to start this off, let's look at an example. And what we have here is the population P of your state is growing at an instantaneous rate of 3% of the population per year. The derivative of the population can be written as dp dt is equal to 0.03p. And this is an example of a differential equation. So what we want to do is we want to go ahead and write a differential equation that describes the relationships in these two problems. So the first one is Alex and Tina have a new Maine Coon kitten named King Robert. Robert is gaining weight, W, at a rate that is inversely proportional, that's important, to his age, T, in months. So our differential equation is going to be the change in his weight over time, so dw dt, is inversely proportional. So we have a constant of proportionality, and it's inversely proportional, so it's going to be over t. So that's going to be our differential equation. The second one, excuse me, your cup of Starbites peppermint coffee is cooling, that's important, at a rate that is proportional, so it's directly proportional, to the difference between the room temperature R and the current temperature T of the coffee. So our coffee, so I'll just use dc dt, is going to be, since it's cooling, it's going to be negative. Here's our constant proportionality, and it's the difference between the current temperature and the room temperature. Okay, so that's the idea of a differential equation. So now, how do we verify what a solution is to a differential equation? So the first thing we're going to talk about are general solutions. And these are considered first-order differential equations because they just are looking at one derivative. And we're going to see we're going to have two derivatives, three derivatives. But the idea is we're going to look at a family of curves that will represent the same situation. And we're going to talk about how we get to a particular solution as we go through this lesson and future lessons. Okay, so we're going to look at some notation methods for representing differential equations. So we have three different notations that we use in calculus. The first one is our differential equation notation, is where we use the slash marks. The second one is our function notation, where we do the f prime of x or the f double prime of x. And then the other one is the Leibniz notation, where we use our dy dx. So any of those can be used to represent a differential equation. So what we were talking about just a minute ago, I was mentioning, is that there's a whole class of functions that can satisfy, if you notice this is the same differential equation, just written three different ways, the solution to y equals e to the bx. So how do we get to there? And then how do we get a particular solution? That's where we're headed. Okay, so what we want to show is that both y equals 2e to the x and y equals e to the negative 4x are valid solutions to the following differential equation. And what that comes down to is we are just going, like you would verify any solution, we're going to substitute and see if both sides of the equation are equal. So on the left side, we have y double prime and y prime. So using our first equation, which is y equals 2e to the x, what we want to do is find y prime, which is going to be 2e to the x, and then y double prime, which is also going to be 2e to the x. So taking those and putting them into the equation, y double prime, so we'll put 2e to the x plus 3 times y prime, which is again 2e to the x we want to know, is that equal to 4 times y, which is, oops, forgot the 2, which is 2e to the x. So we're just going to simplify this. So we get 2e to the x plus 6e to the x. We want to know, is that equal to 8e to the x? And you can see that it is. So this is definitely a solution to that differential equation. And now let's do it again, but we're going to use the other equation, which is y equals e to the negative 4x. So we're going to take the derivative of that, and we're going to get negative 4e to the negative 4x, and then we need the second derivative. So we're going to have positive 16e to the negative 4x. So the question is, does that also satisfy our differential equation? So y double prime is 16e to the negative 4x, and we're going to add to that 3 times y prime, which is negative 4e to the negative 4x, and we want to know, is that equal to 4 times y, which is e to the negative 4x. So let's simplify this. So we have 16e to the negative 4x minus 12e to the negative 4x, and is that equal to 4e to the negative 4x? And you can see we're going to do 16 minus 12 and get 4, so yes. So there are whole families of equations that will satisfy a particular differential equation. Okay, so example 3, that's sometimes what you're asked to do, is to verify with a given differential equation if an equation that you're given is a solution or not. So you're going to go through the steps. So I'm going to do letter A. So we just need y prime. Okay? So, because we have a dy dx here. So dy dx of the given equation we have is going to be negative 1.5. Let me write it this way so you can see where it comes from. This is going to be 3 times negative 0.5 times e to the negative 0.5x, and that's going to equal negative 1.5 e to the negative 0.5x. Okay, so we're going to substitute this into the given differential equation and substitute y on the other side. Simplify the right-hand side and see if it's equal to negative 1.5 e to the negative 0.5x. So is that the same as saying 0.5 times 15 minus 3? Oh, I better use brackets here. I'm going to use brackets because I'm going to have a double parenthesis. So 15 now I lost myself. Okay, sorry. Let me start over here. So that's the left-hand side. Okay, and then I have my 0.5 there. So 0.5 times, here we go, then the 15 minus, and I'm subtracting y, so y is 3 times e to the negative 0.5x plus 15. Okay, so leaving the 0.5 out there, distributing the negative, the 15s will cancel, so I have negative 3 e to the negative 0.5x. Multiplying that, here's my left-hand side, that's my derivative, and that is indeed equal to the right-hand side. So you would say yes, okay, because these are equal. All right, you guys try letter B, and the answer, just so you know, is going to be no for this one. So give that one a try. If you get stuck, we'll do it in class tomorrow. Okay. A function y equals f of t, which satisfies a differential equation, is called a solution. So I talked about the fact that we're going to have general solutions, but we also can find particular solutions using a variety of techniques that we'll pick up as we go along. So for the differential equation, dy dx equals 3x squared, we want to find a general solution. So we're going to just go ahead and solve this with techniques that we know how to do. So we're going to write dy over dx is equal to 3x squared. I'm going to rewrite this. So dy is going to equal 3x squared dx. So now I have two derivatives. So I'm going to integrate both. So I'm going to integrate dy, and I'm going to integrate 3x squared dx. So the first one is being integrated with respect to y on the left-hand side, so I get y equals. And on the right-hand side, I'm integrating with respect to x. So that's going to become x to the third plus c. So there is a general solution to that particular differential equation. Okay, now here is an application problem. You have been given a summer internship at a winery in the Tuscany region of Italy. Your task each day is to track the rate that red grape juice is being pumped into these large stainless steel vats that are shown in the picture. So first thing we're given is the depth y is increasing at a rate proportional, this is an important statement here, proportional to the square root of the depth at any given time. Write a rate equation that would represent this situation. Okay, so the change in depth, so dy dt, is proportional to, so we're going to have a constant proportionality, to the square root of the depth. So square root and depth is y. Okay, so when the grape juice reaches a height of 4 inches, so that's a depth, the depth of the juice is increasing at a rate of 4 inches per hour. What can you find with this information? So here's what we're given. We're given dy dt is the 4 inches per hour, and we're also given that that happens when y equals 4 inches. So what we can find is k, because we can fill everything into our equation in part A. So knowing the fact that dy dt is equal to k times the square root of y, we can fill in 4 is equal to k times the square root of 4. So solving this, we get that k equals 2. So now we can write a more particular differential equation because we filled in our constant proportionality. So our differential equation for this particular instant becomes dy dt equals 2 times the square root of y. Okay, so we're supposed to complete the table below for the chosen depths using this particular differential equation. You notice that the rate the depth of the grape juice is changing does not depend on time. Okay, it really doesn't, because it's not in our differential equation. It depends on the square root of the depth. Okay, so it's 0. When y is 0, the rate is 0. When y is 4, we're going to have square root of 4, so this would be 4. So if you notice, these are all perfect squares, so our differential equation is easy to figure out without a calculator. So then we're going to go 6, 8, 10, 12, and 14. So just taking the square root of each of those numbers and multiplying by 2. Okay, so now the venter needs to know the depth of, that should be grape juice, not water, at any given time. That's why he hired you. What fact do you need in order to find an answer for your boss? Well, what we need is an initial amount of grape juice, because if we can't tell how the depth is changing if we don't know where the depth started. So we need an initial amount of grape juice. Okay, so let's say, suppose we started with 4 inches of grape juice initially. In order to estimate the depth after 1 hour, we will assume that the rate remains constant for the first hour. How do we arrive at an answer of 8 inches? That should be, use this technique to complete the chart. Okay, so how we got a rate of 8 inches is that we want to remember is that when y equals 4, the rate is increasing Let me just fill this in, by 4 inches per hour. So in another hour, so we started at 4 and 1 hour has passed. We're going to take what we started with and add to it those 4 inches. So that's where the 8 comes. And then from there, what we want to do is look at this table above here and look at how much the rate changed. So to go from 8 to 10, we changed by 6 inches. So the next number is going to be 8 plus 6, which is 14. And then we changed by 8 inches. So 14 plus 8 is 22. And then the next rate change was a change of 10. So we're going to go from 22 to 32. And then a change of 12. So that puts us at 44. And then finally a change of 14, which is 58. Okay, so how many functions satisfy our differential equation? And going back to where we started here, our initial differential equation, right here in part A, there is an infinite number of solutions. What information determines what particular solution you'll find? And that is, of course, the initial value. Then we were able to determine exactly how much grape juice was in the vat. Okay, use the data from the second table and plot this particular solution of the differential equation using a blue-colored pencil in the grid below. So what we're going to do is we're going to use this table and plot our solution set. Okay, so I'm just going to go ahead and plot it here without having the table in front of me because it's on the other page. So it is going to look like this. I'm going to use blue pencil, and then we were at 8, and then 14, and then we were at 22, and then after 4 hours we were at 32 or 34, I don't remember the exact number. And then at 5 hours we were at 44, and then we were at 58, which is right up there. So connecting these points, it would look like that. Okay, so there's that. There's what our solution set looks like. Okay, then what we're supposed to do is use a green colored pencil and plot another function that also represents a particular solution of the differential equation. So really what you're going to do is think about if you started with a different amount, your rates are still going to be the same because it's based on the same differential equation. So it's just going to be a vertical shift of that one. So what I did is I just started here at 10 and I just shifted it up using the same rates. So I'm at 4. Move this down a teeny bit. So my last one is like right up there. Whoops. Okay. Okay, so do you notice relationship between your graph solution, and this is going to be our introduction to a slope field. In the background, explain your thoughts. What you're going to notice is all those little lines, this is what a slope field looks like. And it's going to represent all the particular solutions for a given differential equation. So slope fields look like small tangent lines at some x value, or in this case, we were dealing with t, so some time. And what they show is the rates of how fast the depth of the grape juice is changing at a, at a given time. So you can see that they look parallel in a way, but they're shifted from each other. And that's what we're going to see is happening. And we're going to talk more about slope fields tomorrow. Okay, so this is the end of the lesson. And like I said, we'll go over this tomorrow, and we'll introduce slope fields.